All right, so this picture, I kind of spent a little bit of time on it because it's sort of exactly the thing that we're going to hear a lot about when we think about nitrogen vacancy centers in diamond. So the kind of future of quantum sensing is based on this nitrogen vacancy center. So you're going to read a really nice article about this, but color centers in general are fluorescent defects in a lattice. And so generally when we think of a color center, we take some usually wide bandgap material. So we'll call this the valence band and this the conduction band. Here's an energy scale. And I can embed one defect or a cluster of defects, and that can introduce new states within the gap. So here's my filled orbitals. Conduction band's my unfilled orbitals. So normally, this is a diamond. The band gap of diamond is like 5.5 electron volts or something, so it's not very useful for anything. Just looking pretty. But I can embed a defect in there and install a pair of energy levels that allow me to do some fun things. So all of the colored diamonds that you may have seen in real life or in pictures come from different defects being in the diamond lattice. And there's hundreds or even thousands of different defects that have been identified to date in diamonds. And as the importance of this platform in quantum information has become more evident, people are trying to discover even more. So there's lots of theoretical defects, and people are just figuring out how to make them. So the main defect that we think about when we think about defects in diamond and quantum information is shown here. So this is the NV center. And I'm not going to spend a lot of time talking about it today, but I'll just kind of lay a little bit of the foundation. So as drawn here, this blue atom is the nitrogen. And the yellow is kind of my vacancy. So that's the absence of a carbon, and all the gray is carbon. And as it's drawn here, it's implying that I've added a nitrogen, I have a vacancy, not a vanadium. I have a vacancy, and the overall charge on this complex, this nitrogen vacancy complex, is 0. So I'm missing a carbon. I've replaced a carbon with a nitrogen, and nitrogen is in group 5 of the periodic table, and carbon is in group 4 of the periodic table, so I've added one more electron. But overall, that system is neutral because I'm missing a carbon. Is that pretty clear? Okay. So that system, NV0, right, I just said, has one unpaired electron. And that's not useful in quantum information at all. It's useful as an emitter. So if you just want to make a pretty color or make it glow, like that's okay. But for quantum information, we need a triplet, just like we just saw in the vanadium example. So what we do is we apply a potential to shift the Fermi level of our nitrogen vacancy center so that it captures an electron. And that's what makes the very special NV- center, which is an S equals 1, 2 unpaired electrons, ground state. And it has the exact same kind of fun situation that I just laid out in the vanadium example. So it has little m sub s equals 0 ground state, and it has a pair of little m sub s equals plus minus 1 excited states. And in diamond, this energy is in the microwaves. So I can kind of probe or even pump transitions here using microwaves. But normally, just like in the vanadium example, I excite the system using light. I'm not kind of using this little energy to excite the system. I use higher energy light, and then I get kind of natural relaxation processes that populate this state. There's some interesting chemical description of the NV center that describes the nitrogen and the vacancy being bonded to one another. Obviously, a nitrogen can't be bonded to nothing. But conceptually, it's not crazy because there is electron density shared between the two sites. So the field of physics and biology have really gained some appreciation for this defect pair as a really transformational tool in both biology and physics. So biologists have found that, in particular, diamond nanoparticles can be used as very robust fluorescent sensors in vivo. So you can kind of put 4 nanometer nanodiamonds in cells and organisms, and the optical transition, the kind of fluorescence, like in the vanadium picture, can be used to do chemical sensing. And then physicists, on the other hand, have made tremendous progress in understanding and controlling the electronic properties of single impurities. So instead of having maybe a collection of impurities in their diamonds, they've tried to isolate just these single species, either chemically through synthesis or optically just through how they detect and excite the system. This nitrogen vacancy defect is magnetic, as we just described, and it can show kind of quantum behavior up to room temperature, which is kind of the thing that makes it really exciting. It has very long coherence times at appreciable temperatures.